Hello and welcome. My name is Matthew Carpenter and I'm making this video to show you a project I'm working on in Max MSP. The goal of the project is to create a perpetual generative music system modeled after wind chimes. I chose wind chimes because they're a physical generative music system responding to a source that's non-musical and unpredictable, but not random. When you think about the wind, it's arrhythmic and irregular, but nonetheless it follows an invisible pattern. So that's what I set out to simulate in this project by creating an instrument that responds to an invisible modulator that's irregular but creates music. So let's get into it. Starting at the top, we have two oscillators. The first is a phasor oscillator, which is going to send out a ramp of values between 0 and 1 at a rate of 0.05 hertz. And when it gets to 1, this is going to reset back to 0, which we'll use to generate an impulse later on. The noise oscillator is sending out a continuous stream of random values from a range of -1 to 1. And we're going to pull both of those into the gen patcher here, where in inlet 1 we are subdividing that phasor ramp by 128. This could be any number, and it's going to be the rate at which we want to modulate the wind oscillator. So what we're doing is using the latch object to sample the output of the noise oscillator at the rate determined by that subdivided phasor using those impulses. And then we're going to multiply that by the slope of the phasor ramp to essentially scan through the phase of a sine wave down here at the bottom of the cycle object. So we can see this visually by looking at the output of the gen oscillator. And what you have is guided by a sine wave moving slowly from -1 to 1, but among that movement you have all of these swells and hills that are unpredictable. So what we do with this data is first pull it into this chimes subpatcher. And what we're doing in here is kind of modeling the position of each of 5 wind chimes virtually. And the first thing that we're doing is we're going to scale the signal value from a range of -1 to 1 to a range of 0 to 60. And that's not a necessary step, but it kind of helps with the logic of thinking about what we're doing next, which you'll see at the top. Each of these signals, for each of the 5 chime models, the signal is coming in twice. Firstly through this kind of threshold operator, which will send out a 1 or a 0 depending on whether the signal is greater than or equal to, depending on the operator, that signal. So in this case we're getting a 0, changes to a 1, and this will open a gate that allows for an impulse to pass through, adding kind of an extra conditional to be met for impulses to actually strike a wind chime. And firstly, in each of the models, we're just bringing the signal directly in, and we can see inside here. What we're doing is, of course, passing an impulse through the gate through output 2 to trigger a wind chime if the event occurs. but through output 1, we're generating a list of 3 values. The first of these represents the delay, which we'll get to in a second. Secondly, we have the voice number, which is determined by this probability object. The probability object, you can see here, given an impulse, spits out a number between 1 and 25 based on a probability matrix set up beforehand. And that will be important in the next step when we are mapping each of those to a frequency. Lastly, in this list, we have the velocity, which will affect how loudly or how hard a chime is struck. So from here, out of output 2, of course, we have an impulse, which is being distributed to not only strike a wind chime, but also update other parameters outside of the subpatcher. And then we're sending that list of values out, preceded by a target message for each voice within the mc.poly object. And what's happening here is we have one patcher with 5 voices to represent each of the 5 chimes. So this is a bit of voice allocation to ensure that each model makes it to its own voice, and we're able to have the polyphonic sound. Inside of mc.poly, we are bringing in that list, and firstly, this is going to go, the first number, that delay, is going to set the delay time in milliseconds of this del object. And what that does is whenever there's a chime struck, it has the potential to hit an adjacent chime, and this will be setting the delay time in which that might occur, kind of the time that it would take for one chime to swing into another. Secondly, of course, that voice key. We're filtering out repeated numbers so that we don't have a lot of feedback or cascading activity. And as I mentioned, each of those voice keys 1 to 25 is mapped to a frequency. And we're doing that in the dictionary object here. And if I give this an impulse, you can see that 1 equals 880, 2 equals 440 hertz, etc. And this whole setup here generates this dictionary every time that you open the patch. So it looks like this for me right now, but it will be different next time I open the patch, and it'll be different if you open it. And of course, we could change some of these values to have any number of frequencies available. As of now, we have 25 keys and 5 values repeated 5 times, so there are 5 ways to strike each pitch. And lastly, of course, we have the velocity value coming through, which you can't see directly because it's only being updated given an impulse, but that is essentially placing this point in our amplitude envelope, determining how loud or soft a certain instance of the sound will be. And the amplitude envelope, of course, is affecting a simple little FM synth here. We have obviously the carrier frequency coming in from the dictionary object, and we're multiplying that by 2 to achieve the modulator. And the modulation depth is being controlled via this input 3. We have just a scaled version of the parent wind oscillator. A little low pass filter, and that's about it for the synthesis. We're next going to pull that 5-channel audio signal. This was the purpose of using mc.poly. We're going to bring this into mc.gen. And what we have here is a simple build of a Schroeder reverb, which is a technique developed in the early 60s and requires running your signal through a series of all-pass filters. And what that means is we are bringing that audio signal into one of these gen subpatchers, delaying it by a very short amount of time, and feeding it back into itself. You do this 10 times over in series, and it creates kind of a smear or a elongation to the transient, and begins to sound a little bit like a reverb. And you add this next step, which is pretty similar. It's a feedback comb filter, where we're also delaying the signal and feeding it back into itself. But we do, in this case, 8 of these in parallel. And by doing that in parallel, we're kind of mimicking different points in a physical space where sound might reverberate. So again, 8 times over in this case. Bring all that into a matrix mixer where these signals are going to be combined, inverted, multiplied in all different ways to essentially just create complexity in a stereo image. Of course, we're mixing that with the dry signal and we're sending it out, and it's going to 2 places. That pretty much wraps up the audio side, so we're just mixing it down to 2 channels, and we have our left-right stereo image. But we're also sending that signal, that 5-channel audio signal, to this visualizer subpatcher. Now, in most of the visuals are contained in this area of the patch, especially in this subpatcher, and it has 3 inputs. We have, of course, the 5-channel audio signal. We have this floating point number box, which you may remember from the beginning. This is controlling sort of how high these peaks are in the visualizer. And of course we have a toggle to turn the whole thing on or off. And there's also this blue cable that says jit.gl.texture. And we'll get to that in a second. Inside the visualizer patch, we have first jit.world, which is the parent context for everything going on visually here. Secondly, we have that multi-channel audio signal being unpacked to single signals. Lastly, we have the height parameter being distributed to all of these subpatchers. And once again, we have a little bit of voice allocation, since we need to generate a jitter matrix, or like a jitter context for each of these lines that we want to represent visually, each of the chimes. We have a bit of redundant patching that allows me to make an edit to one of these and it applies to the rest based on the input. But the most important part of this patch is this PFFT subpatcher called WC Spectrum. And what's happening in here is we're performing an FFT analysis of the incoming audio, which gives us peaks at the frequency and amplitude of peaks in the audio signal. We are using jit.poke to apply that to a jitter matrix, which essentially just lights up according to incoming frequencies. From there, we are bringing it into jit.gen, where we are using that to remap the coordinates of a normalized set of values. Essentially, this is generating this like black and green gradient at the bottom, and what we're applying to it are the pink lights that you see. We do this 5 times. And then we're also sending out this texture. And what's coming out of this cable is the full visual window, everything that we are seeing visually. So out of here, first we have the GL paths subpatcher, which is bringing the output of jit.gen from the previous subpatcher, the black and green gradient, into jit.gl.path, which uses that matrix to generate the lines that you see in the window. And those pink lights that we made before are now represented as these swells in the lines. The rest of the objects in here function to modulate the position of the lines, and just kind of keep things moving, create visual interest. And all of that modulation is coming from the parent wind signal. And lastly, that texture is coming out of the last outlet here, and we're bringing it into jit.gl.pix, which has 2 parameters coming in. The first affected by the parent oscillator or modulator, and the second is here from the beginning, and that is the level. Because what we're doing here is essentially just a little visual feedback. It's a lot like the reverb technique, where just taking the whole image from jit.world and scaling it up or down and feeding it back into itself, making it larger or smaller and feeding it back through. So if we turn this all the way down, you'll see only the lines generated by jit.gl.path. But by turning this up, we get this cool echo effect and some moire patterns. And that pretty much covers it. We have, a few other a trigger object here to kind of ensure things load up properly. But yeah, there will be a full render of this patch, or a longer video of it just operating up on my channel. The patch itself will be available on my website if you want to play with it. And if you have a question or comment or critique, suggestion, please reach out. And thank you for watching.